Okay guys, here we go. Lecture 7, talking about the fundamental theorem of calculus. So in the last lecture, you learned how to approximate the definite integral, which represents area under a curve, using Riemann sums. And that very last example that we did showed you how to find the exact area under the curve. Well, what I didn't show you is how to actually find that limit that we wrote down in example 5. And to be honest with you, it's a very tedious process and not something that is very much fun. And so because of that, the mathematicians way back tried to figure out an easier way to find the value of a definite integral without having to compute the limit of a Riemann sum. And what they found was absolutely just the most beautiful theorem in calculus, which brings together the concept of derivative and integral. So that's the fundamental theorem of calculus. It says the function is continuous on a closed interval from a to b. Capital F is an antiderivative of f on the interval from a to b. Then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. And so basically, in order to use the fundamental theorem of calculus, you first have to find an antiderivative of f and then evaluate that antiderivative at the upper and lower bounds. Okay, so guidelines for using the fundamental theorem of calculus: provided that you can actually find an antiderivative of f, which is not always possible, you now have a way to evaluate a definite integral without having to calculate that ridiculous sum or a limit that we found in the last lecture. Now, when applying the fundamental theorem of calculus, the notation that I'm going to use is the following. So let's say, for instance, I have the integral from 0 to 3 of x to the 4th dx, just for example. Well, the antiderivative of x to the 4th, remember from a previous lecture, is 1/5 x to the 5th. I'm going to draw a vertical bar here with a 0 at the bottom and a 3 at the top, and what that means is I'm going to evaluate from 0 to 3 and then plug in using the fundamental theorem of calculus. Sorry, that should be a 5. Okay, and it is not necessary to include a constant of integration in the antiderivative like it was when we did indefinite integrals back in lecture 5. Okay, so example 1, we want to evaluate the definite integral. So the first thing I have to do is I have to find an antiderivative of the function. So in this particular case, the antiderivative is going to be x cubed over 3 minus 3x, and I'm going to evaluate that from 1 to 2. And so if I plug in 2 first, that's going to be 2 cubed over 3 minus 3 times 2. Okay, and I'm going to put that in brackets just so that I know that those two terms go together. And then minus, from the theorem, bracket, I'm going to do 1 cubed over 3 minus 3 times 1. And if you calculate that, you're going to get negative 2/3. Okay, so find an antiderivative, plug in the upper bound, subtract, and then plug in the lower bound. Okay, well, in example B, in order to find the antiderivative, the first thing I need to probably do is rewrite this as 3x to the 1/2 dx. That way I know how to use the power rule. And so this is going to be 3 times 2/3 x to the 3/2 evaluated from 1 to 4. And if you want to clean up those constants before you plug in 4 and 1, I would recommend that. And so this would be 2x to the 3/2 evaluated from 1 to 4, which is going to equal 2 multiplied by 4 to the 3/2 minus 1 to the 3/2, which, if you calculate it, is going to be 14. Okay, now you do need to be able to do that without a calculator, so let me maybe just talk about how to do this 4 to the 3/3 term, okay, without the use of your calculator. So maybe back up here, 4 to the 3/2. Well, in order to do that, what you could do is you could cube 4 and then take the square root of it. Well, that's honestly not too hard in this case, but sometimes when those numbers get large, you're not exactly sure what to do, and they get too big that you just don't know them without a calculator. So instead of cubing 4 first, take the square root of 4 first, and then raise it to the 3rd power. Okay, so in that case, 4 to the 1/2 is 2. And if you cube it, you're going to get 8. So that's how I got 8 here, minus 1, which was 7, and then multiplied by the 2 gave me the 14. Okay, so just make sure that you can do those basic arithmetic things without the use of your calculator. Okay, example C, we need to find an antiderivative of secant squared x dx. Well, my derivative rules, my knowledge of derivatives should help me remember that tangent x has a derivative of secant squared x. And so in this case, the antiderivative is going to be tangent x, evaluated from 0 to pi over 4. Okay, so if we plug in our upper bound first, we're going to have tangent of pi over 4 minus the tangent of 0. And in order to get this problem correct, you have to know the unit circle. So that's why I gave you assignment 0 to help your unit circle skills. Tangent of pi over 4 is 1. Tangent of 0 is 0, and so the answer to that definite integral is just 1. Okay, part D, the integral from 1 to e of 1 over x dx. You should hopefully recognize this as being the same thing as x to the negative 1 dx. And if I try to bump that up and divide, I'm not able to do it because it increases to 0 and I can't divide by 0. So that should hopefully make you remember that this is a different rule. And in this case, it's the natural log rule. So ln of the absolute value of x, evaluated from 1 to e, is going to equal the natural log of e minus the natural log of 1. These are also two values that you need to have memorized coming into calculus. And so natural log of e is 1, and natural log of 1 is 0. And so the answer, again, is 1.